Good morning. Today's lecture is the first of a series about materials and systems. So today we'll start with masonry. And what I'll do is to follow this type of logic. So I will show you some examples and types and wall details, and we'll go through the manufacturing process. And after that, the second part of the lecture will be about architectural examples and a bit of discussion about how masonry has been used in architecture. All the lectures related to materials and systems will be based on this type of structure. So first we talk about construction, details, manufacturing, and then we talk about architecture. Right? But as usual, I think I'll start with a short story. I don't know if you've read Invisible Cities, the book by Calvino, 1972. In that book, I just quoted a small part of it, which says that there was, you probably know what Marco Polo is, an Italian guy who used to travel in the 13th century in Asia, and then he came back with a set of knowledge. And in this dialogue, in this book, this is just a conjecture. It doesn't exist at all, but he used to take Marco Polo as a character for this book, and he was talking to Kublai Khan. And Marco Polo is describing a bridge, and he's doing that like stone by stone. But Kublai Khan asks, well, which is the stone that supports the bridge? And Marco Polo replies, the bridge is not supported by one stone or another, but by the line of the arch that they form. Today we would say that's the thrust line. So Kublai Khan asks again, why do you speak to me of the stones? It is only the arch that matters to me. And Marco Polo answers, without stones there is no arch. In some ways this is the approach that we should probably have here in this subject. That, of course, it's important, the geometry and the design part, but if we don't really know what the stones are and how they are made and how we get them to the specific shape, we will never be able to do the arch. And most of the architecture we see around is actually built, so a small part of it is conceptual. In order to complement this small story, I decided to put a couple of pictures related to the Castelvecchio Bridge in Verona. It was an excellent bridge, which was one of the several ones demolished during the Second World War. And these are photos of the reconstruction, so that you see centrings and scaffolds ready to accommodate the stones of the arch. But what we will cover today is this. So I'd like to start a small story about stones and bricks. So we'll talk about dry construction first, in stones, natural stones. Then we'll talk about stereotomy, which is an art related to cutting stones to size. Clay masonry. From clay masonry we'll go to mortar, masonry units, and differences between bricks and blocks. Having done that, we'll talk about the brick veneer, which is rather diffuse in Australia and also in some of the houses that you might have as a case study. The bond types, details, how to make openings, and then we'll talk about the concrete blockworks, so the wall types, joints, how to turn corners, these type of things. Then we talk about the lightweight version of that, so the AAC, okay, autoclaved aerated concrete. Again, wall details, how to make seals, linters, how to insulate it. You will see that somehow the rules are more or less similar for all of them. And the second part of the lecture will be about some architectural examples. I won't start from the past because I'll show you some examples at the beginning straight away. But we start, let's say, with the Expressionism, Modernism, Postmodernism, and we can go even towards not standard architecture, but I didn't place any examples today because we spoke about that last week. But again, if you would like to have a better insight of what we are talking about, there is this book, Masonry Construction Manual. Unfortunately, for what I could see, in our library is only in German, because I think that was the original version, but however, I found an English version online, so I'm going to upload it on the LMS, even if I'm not sure I have the rights to do so, but I will upload it anyway. I didn't prepare the lecture out of it, but I took, as usual, some slides, some sentences. So if you really want to have a better understanding of masonry, you can just browse this book. And you need to be careful about the details, because this was written by a Swiss guy, the German part of Switzerland. So you will see that all the drawings, details, standards are related to Europe and particularly to Switzerland. So you will not find anything related to the Australian standards. So if you feel confused about that, just know that it's because it was written from another country. And that's why one of the main difficulties that we have in providing you books coming from overseas that really refer to different standards and uses. But let's start with the small stones. This is an Italian example from Sardinia, a small island in the Mediterranean Sea. What happens? This is called nuraghi. It's a vernacular architecture. Dry construction means that there is no bonding agent, so there is no mortar. The stones are placed one upon the other just due to self-weight and shape, right, and friction. So there is no bonding agent, there is no glue, if we want to speak in plain terms. In this case, you see that at the same time it's easy because you just collect materials that you find naturally, but at the same time you need skilled labor because you need quite an organization to place. You see the larger stones are at the base, and then you need to make sure that they can actually interlock, so you need to test them and make sure that you can build something out of them without cutting them to shape. And then once you reach a certain height, you start putting smaller stones, and probably you see that the shape is slightly tapered. Probably the aim was try to, of course this is a tower, kind of a protection wall, but at the same time the overall idea was probably to try to get a kind of roof. And as far as we know, there probably was also a floor in that, a timber floor, which, because of the material properties, didn't last. So we don't have it yet. But it's a conjecture that there was a timber wall in the a timber floor in the past, in this position, this level. You see here the detail that actually the stones are not cut to size. It's just a patient work and of an expert person who's actually sitting there and trying all the possible combinations. Still, you make this wall happen. So it's really at the same time primitive, vernacular, but very difficult. A little bit more sophisticated is the Roman and Greek construction. In this case, we could talk about stereotomy because you see that in this aqueduct, the stones are already cut to size. They are very precise. And this is an art. This is called stereotomy. Stereo means, in ancient Greek, the etymology is solid, kind of solid. And tomos means cut, split. It's something that you use also when you have very large books. You divide it in small tomes, so this means split. So it's the art of drawing and cutting stones to complex and precise geometries. In some cases, this is not so easy because when you want to draw an arch like this, which you see, it's a new thing that we haven't seen in the previous example. These stones cannot be cut, just as rectangulars. They have to be cut with precise angles. In other cases, when you want to have complex vaulting systems, then it means that you even need to cut them in more complicated ways. So you really need to master geometry and some basic tools on how to mark these elements before cutting them. So somehow it's this is already, let's say, a more sophisticated and we could say engineered usage of of dry construction. How many other sophistications you see in this example? I could list at least other two. The first one is that the columns are actually tapered. So you see they reduce in size. And the last one is much more slender than the previous one. This is to try to reduce at the same time the self-weight in order to have material just where you need it to support structural loads. Another thing is that this structure is repetitive, is modular. So you see you have always the same bay and you repeat it several times because the Romans were very good in doing arches. So what they did in most of their architecture was to repeat arches throughout the project. You see a detail here? No mortar. So this is not fake, it's real dry construction without mortar. But you see the level of precision of this one compared to the previous one. Stereotomy is still used nowadays, in the south of Italy especially, or in France somewhere. Building with stones is still a natural thing, and it's a very diffuse material, and they really want to do something with that. So there is a research group at the university in Bari. They are working on trying to use stereotomy to rebuild some architectures of the past in a more interesting way. They're also working on defining something completely freeform. But I'm just showing you these two examples of, these are French vaults, French vaulting systems. They're called Abbaile vaults. So it's A-B-E-I-L-L-E. And you see the cuts of these stones are already more complex. When you want to have almost a flat configuration like this, it's kind of easy. But when you want to have a triangular configuration, doubly curved like that, it becomes more complicated. So the way to cut these things is becoming more complicated. It can be done nowadays through digital fabrication, so it can be done numerically. But I placed a link here so that you can just go on the website, because there are videos, photographs, and a lot of things that you can look at on your own much better than what I could show you here. Another ways of using stones, let's say a dry construction technique, is this one again in the south of Italy, Bari, because again stone is the most important material. This is a church designed by Renzo Piano, and in this case there are several arches. And the point is that, of course, they are compressed with some tension wires which are running inside the stone so that they keep all the units in position. But somehow we could say this is a dry construction, very engineered one, but dry construction. But somehow it's difficult to say if we started building in masonry using stones, natural stones, or bricks. Probably bricks, because natural stones are very heavy, they require skilled labor, very difficult to build a wall out of that. But with clay masonry, everything becomes easier, because you just form them out of clay, you let them dry under the sun, you can keep them in your own hand, so you can hold a brick with one single hand, so somehow everything becomes easier, even if it looks more sophisticated in manufacturing process. But the construction is rather simple. Already you see these are the granaries of the pharaoh tomb, so this means that 3,500 years ago they were already mastering this type of techniques, and they were able to construct a vaulting system without centrics. So there were no scaffolds to do that. And this is because, if you look at the picture on the right, you see the courses of the bricks. They are slightly inclined. So because of this inclination, they were actually able to construct that vault without any support, just brick after brick. I'm showing you some details. So that's the whole idea. You have a supporting gable, a wall here at the end, And then you use these 3 wires to trace the line of the arch. And because of the mortar that is very sticky, and also because of the shape itself of the arch, which is almost a catenary. And a catenary is the shape that you would get if you just take a chain. So just an element without rotational stiffness, like this one, and you just let it take shape under gravity. So that type is called catenary, from the Latin catena. You see, but really the trick here is the inclination of these courses. That due to this inclination, you can actually place mortar on the bed and perpend, and then you just put the brick there and you wait a few seconds, and then you place the second one, the third one, and you go course after course to make the vault. So you start on both halves at the same time, and then at a certain point when they meet, when they touch, then you put courses in the horizontal way, and you've done it. So this was already well known 3,500 years ago. And even in Iraq, now it's, this unfortunately is almost destroyed. Considering the political situation of the country, there is not really any concern at the moment of preserving these. There are many other issues, but this was an incredibly wide, an incredibly large span, entirely done in masonry, and again, more than 2,000 years ago. So this type of techniques were clearly mastered already in that period. The right side, which is not present in the photograph, and also this one is a reconstruction. Actually, this was almost all destroyed during the war, and the arch is one of the few parts remaining of the building, of the original one. In the 19th century and then the 20th century, this type of vaulting system became engineered and mastered from the mechanical point of view. The most important person who did that and who worked on that is Guastavino. So that's why we call the compression-only vaulting system and shell system, we call them Guastavino vaults. This is an example of a stair done by Guastavino, and you see this is a vault. All this is an actual vault. It's a compression-only situation that he was able to get out of a geometrical operation. So he knew how to calculate the thrust line, so exactly where the forces, the compression forces, go through the structure just through a geometrical process. That is called graphic statics. We don't go through that, but it's very interesting to see that it found a new research stream recently due to the introduction of parametric design, because this type of geometrical things can be parameterized very easily. So there is a research group now in Switzerland at the ATH, led by Philip Bloch, and what they do, they reconstruct Guastavino vaults, but in free forms. So they start from free forms and they try to readapt those shapes in order to be compression only, and also in order to place the masonry units in such a way that they are that's the most efficient way for them to perform structurally. This is one prototype they did a couple of years ago, and they're also working on actual projects. Philip Bloch is more or less my age. We did the PhD together, so it's a fairly new thing. He started in 2007, and I remember his lecture when he got the book from the library talking about graphic statics. And look back at the, at the end of the book, so you always find the list of people who borrowed that book before you. And the previous one was probably more than 50 years ago. So it was a bit scared about this type of research. Probably it wasn't useful at all, so no one cared about that. But in some cases, when you discover something that hasn't been read for a few years, then it might be more interesting in what you think, and you can reuse it properly. But let's talk about clay masonry. What is that? We're talking about small bricks that you get out of clay, and there are a few advantages. So the first that I already said, they're small enough to be held in one hand. So you form them, the shape you like, and therefore what you do, you make sure that you can actually keep them in one end so that you have the second end free to place the mortar, so that you can work with both ends. All right? At the same time, it's also interesting to notice that small bricks combine well with concrete and stones, and you can build very large structures out of very small units. So with something that you can hold in your hand, you can build this type of Basilica di Massenzio, for instance, in Rome, or these imperial baths, where you see again the arches are placed one on the other. There is a combination of clay masonry, stones, and this is really, let's say, an improvement of the way masonry was used. Structurally speaking, the most common diffuse typology in the period of the Romans was the cage. So you see the first one on the left. So you see structural walls in both directions so that it is laterally stable. But with masonry, with structural masonry, you can actually do other things. You can have modular constructions so that you get this type of spines, and then you have infills, so that it's completely open, not structurally, can be completely glass. Or there is also another interesting use, this, again, elements in both directions so that they are laterally stable, but at the same time irregular. This type of configuration has been used several times by Mies van der Rohe and by Frank Lloyd Wright to divide spaces. So instead of placing a door, what you can do, you just get a very wide space followed by a narrow space, and then again a very wide space and a narrow space. So this is the way to create rooms and spaces without actually using a door or separating elements in that way. Somehow Zaha does that. She's more following flows, so you don't really see this type of interactions in orthogonal directions, but I think it's the same idea, more or less. Hybrid systems as well. And then the mortar. This is really one of the most important things in order to achieve an acceptable level of structural capability. And we could say that mortar is the glue. Just simply speaking, is the glue of masonry construction. When you bond together two different bricks, with that then you get a monolithic element, like if it was concrete. And another thing you can use with mortar, sometimes if you use small stones or if there are imperfections, you can seal them. You can actually make sure it comes back to a very precise courses, and you can lay the bricks precisely because the mortar allows you to correct those type of imperfections. And traditionally it was obtained as a mix of lime, sand aggregate, and water with lime. So the lime is the bonding agent, sand is the aggregate, and water is to mix all together. In contemporary construction we also add cement, so that there is a different structural capability, and this also affects the color. So color is mainly affected by one thing, the sand, so that is the aggregate. Depending on the type of sand you use, you can get a different color, or you can add extra pigments. So if you add pigments, you can get more or less whatever color you want, but you are going to make the mortar weaker. So it's always better if you can play on finding a different type of sand in order to change the color, rather than using external pigments. Mixed design and classes. What is mixed design? Mixed design is the procedure that you use to combine these elements together in different proportions. It's actually like preparing cocktails and mojitos. You need to know exactly how many parts of which element you need to make, you need to put together and mix in order to make the right, to get the right type of mortar. The Australian standards have actually classified these in different classes. So you see the source is here, AS 4773.1, and there are also others, okay? And what you'll find there is that the unit is always given by cement, so you compare the others against cement. So you can say, I have 1 unit of cement, and I need to add 3 units of lime and 12 of sand. So that's the way you actually describe a mixed design. And you do that also just using the initial of the ingredient. So you just say C1 together with L2, so 2 parts of lime, together with 9 parts of sand, S9. All right? So very not too difficult. And just to simplify, M1, you'll never use it. It's mainly for restoration works. In interiors, you generally use M2, and the ordinary for structural purposes is M3. So these are the type of things you're going to use. And for very special uses in marine environment, which are aggressive, then you could use M4. But let's say M2 and M3 are probably the type of mortars that are used in all the case studies you have. Any questions so far? Great. Color, as I said before, the mortar can actually have a significant impact of the final aspect of the wall. You see here there are brown, light yellow and red bricks, so different type of clays, and I'm comparing a light and dark mortar applied to the same system. So you see left compared to right, and it actually changes a lot. So just make sure that mortar is not a secondary thing, that you just get whatever comes. It's really important that this is again an integral part of design, and you make some mock-ups. Most of the times you make a mock-up of just to understand how it looks and to combine colors properly. All right? As I said before, you can get a color out of, for instance, white sand or a different type of sand rather than using external pigments. In other cases, when you really want to get a red or these type of things, you need external pigments. Measuring units. So how do we classify them? In books, you will find very different classifications, but more or less, we could always say that there are 2 main families, man-made and natural units. So bricks, clay masonry, these type of things, we are man-made. Natural stones are natural, so you just find them in nature as they are and you use them as they are. So the first one goes through a manufacturing process, the second, they're just collected, and maybe they're cut to size. But when we have man-made units, we could say, and this is what I'm going to talk about, that we have clay bricks, concrete blocks, which are a bit wider and bigger, and we can have 3 types of sections, so solid, cord, and a hollow section, so that is more lightweight. The solid one is, of course, just, very conventional bricks. Sometimes you find this indentation, which is called a frog, just because you could, this helps the mortar bed to bond one brick together with another. In some other cases you don't need it, but most of the times you find it. Then you have a cord brick. Again, there are 2 purposes. The first one is to have a better grip with the mortar, and the second one is that it's lighter, so you just reduce self-weight you won't need. The third one is hollow. This type of profile is mainly done when you have a concrete blockwork because it's more resistant, and therefore you can remove much more material out of it. What is the main difference between bricks and blocks? Well, the main difference is in dimensions. Of course, the difference is also in the material. But there are also blocks done out of clay, but in Australia you'll always find them done out of concrete. But clay bricks are the most common ones, and the standard size varies from country to country. This is the one related to Australia, so this means that 23 centimeters by 11 by 7.6. And why this type of units? Because they were originally designed according to the imperial units, and then they've been converted to the metric system. That's why there is this odd number, 76 and 120. And generally you have a mortar bed, which is the horizontal line here between two bricks of 10 mil, and perpends, which is the vertical line between bricks, called perpen, between 6 and 10 mil. Concrete blocks, again, they have another specific standard in Australia. It might vary in other countries. Like, for instance, bricks in Italy are generally 12 by 24 by 6, so that they are always proportional, and you can actually interlock them well together. The Roman bricks are even thinner, slender, so it really varies on the country and on the use. Having this type of height saves you a lot of work, because one brick it's already occupying 7.6 centimeters, so you need less courses to make up your wall, so less labor. I think that was the purpose when they decided that. The standard block is 39 by 19 by 19, and again the mortar bed is about 10 mil. How does the manufacturing process work? There are two main ways. The first one is what you see here. It's still common in a few countries, like in Pakistan. This photograph on the right is from 1999. But that was the way it was done by the Egyptians and the Romans. They were actually formed, so they could actually dig clay and form them, put them all on the ground to dry under the sun, and then you just get the bricks ready to use. So that was a very manual process. Now it's completely industrialized, and this is the scheme, the manufacturing process that you get out of one of the most important companies, Boral, from the US. But there is one important thing to say. Clay is at the same time one of the most abundant materials on Earth, but it's also very heavy. So it's unlikely that you produce this in China and you transport it to Australia. You produce it locally. It's not like steel, glass, or other materials. It's impossible. I've never seen anyone importing bricks from Europe. You produce them locally. They are too heavy. All right? So they're generally very close to the cities, the companies doing that. And if you want to have a better understanding of how this works, on this source, Boral, there is a video of the manufacturing process, which is mainly divided in 6 phases. So what happens is, I try to clarify a little bit this scheme for you. So actually mining and storage of your raw materials. So you need clay to produce bricks. The second phase is that you need to prepare raw materials. So you need to make sure that they are clean, they have no other materials on it. So that's another second phase that you need to perform before actually forming the bricks. The third one is the most interesting, because you see they are actually done through extrusion, and then they're cut to size using wires. So here they are extruded, and then if you need a particular texture on the face, you apply it with some stamps at this stage here. Here you cut them to size, and then they go to the fourth phase. They're ready to dry. Once they're dried, then I don't know if you can say that, you cook them. There is the firing and cooling phase where you actually cook the clay and you get also specific color. According to depending on the amount of time you leave them there, you can get them lighter or darker. All right, so this is a phase that can affect the final color of the bricks. And the final one is storage and shipping, so ready for distribution. So these are the 6 phases more or less all the companies use to produce masonry. Okay, now more difficult thing. You will find a lot of handbooks and manuals for carpenters which explain clearly how to make a brick veneer, And apparently, you followed these 10 phases, and it looks rather simple. I bet I tried. It's not so simple. You need to be kind of expert, particularly not to waste and put mortar everywhere, and to make sure that the courses are actually straight. But the first thing you do, you take your left hand. It depends if you're right-handed or left-handed. If you're right-handed, you take your left hand and you take a brick. Then with the right hand, you place mortar on the perpends and on the bed. And then you make the first course. When you arrive to the second course, you need to make sure that the brick is actually centered against the first one. So you place one brick vertically to make sure that you have a guide to place the other one. You see here there is a wire. This wire is used and is moved course after course to have an indication of what the height and what the level of that course should be. Otherwise you will never get it straight. So you always use a wire to guide yourself. So the first thing you do, you also place mortar here, number 6. You place the mortar also on the previous course of bricks. And you just put the brick in place, and then you adjust it. You just pick it slightly, okay? And then you adjust it, and you clean up the exceeding mortar. Then there is also another phase that you won't see here, but you can actually change the shape of the final joint, so you can clean it up even further. And there are also different bond types. So these are the two most common. So we've got stretcher, so just courses of bricks in which every second the units are shifted. Another very common one, the English or Dutch bond. So every second course, you just rotate the units in order to show the head of the brick. And these are common things that you probably see on campus. There are more complicated ones, more interesting ones. They become ornamental. And I think in this case, it really depends also on the type of shape of the wall, or if you're actually using masonry to make a column. In some cases, the diagonal stretcher really emphasizes the shape, the circular shape. Probably don't worry, because there won't be an exam, a question on the exam asking you to remember all the different types. But it's good to know that you open the handbook and you find all of them. So whenever you need inspiration, or you need to understand how these things could be done, you can always open the handbook and you find an infinite series of different types. So you see here, this is a kind of diagonal stretcher, a variation of that. We've got a column, and this diagonal stretcher emphasizes the circularity of that element, all right? Make it more dynamic. There are also other ornamental bonds, so which means that you can actually remove some elements, place some others in relief. You can make combination of things. They can be used to ventilate interiors. You remember last week I was showing you this parametric wall by Gramazio and Kohler. The system was very similar to this one on the top right, but then it was, how to say, slightly rotated and translated according to a specific Gaussian function. Again, how many different bonds and ornaments you see in this one? If you can list now all of them, I give you 3 points. But all of them. But yeah, just to say that between the Middle Age and the Renaissance, they were used quite often. So I think it's really a guide for you to understand how masonry was used. Most of the times you think that masonry is an element that is quite boring, repetitive, modular. So you're forced to get these very monolithic things. But in most of the times, masonry has been used to liberate the architect's ideas and creativity to create very interesting ornaments. So I think it's a nice contradiction. Now let's go back to your case studies. This is more or less the typical detail you find in Australian houses of the brick veneer. Remember this because this is very important. We always put it in exams and things like that. So it's very important to understand how this section works, but more important is to understand what the principles behind this section are. Because if you know what they are, you can reapply them to another section and understand if it works or not. My suggestion is that you look first at the structural elements. Where are the structural elements? Well, the structural elements are hidden a little bit behind this insulation. We see the bottom plate of the stud frame here. We see a kind of noggin here, but the stud, the vertical one, is hidden behind that insulation. That's the structural element number one. Without that, we are not able to sustain the wall and the upper floor. So first we need to make sure that there is a structural element. All right? Always, when you look at a cross-section and you want to understand how the section is done, find the structural elements first. Make sure that there is continuity so that the structural loads can go from the top towards the footings and then again to the ground. So first find that. The second element we need to place is protection, a barrier. So we need to protect the structure, the insulation, and all the other things. So the second thing we need to look at is the waterproofing and the vapor barrier. And it's this line here. So you see it's placed on the external side of the wall because this is meant to protect the structure. All right? So it's placed here. If this is a waterproof layer, it means that water can actually go there and then it's going to be collected down here. And then there is this let out, this flashing. This is that just a dashed line here. But this is a metal element that is able to collect water and bring it out. Here there is a weep hole. So you see that there is a continuity in waterproofing so that water cannot access the house. Then other things we need to look at, we could say conceptually, filters. So something that is able to mitigate the environment. So here is very cold and here we want a very warm environment, or vice versa. It's a very warm summer and we want indoor a nice and chilly environment. So what we do, we place insulation generally within the stud space and it's protected. Then we have two other things. Finishes, so we need to, again, either protect or have a final architectural expression. So inside there is like plasterboard and lining, or there could be render or other finishes, but somehow we complete the wall placing that layer so that we don't see the insulation. We cannot touch and access the insulation. All right? So we protect it, but at the same time, it's an architectural expression because that's the way we want to see the wall. On the outer side, there is the brick veneer. So the brick veneer is not a structural element, it's just meant to self-support the wall. So it's self-supporting, all right? And it is connected to the structural elements with these ties. So you see here there are ties that at the same time connect the wall and make sure that it's laterally stable, but also they make sure that there is a joint, because these two layers, these two lifts can behave in different ways. So let's say that there is some just heating this wall, and this can expand and can behave differently from the internal structural layer. So through these ties, they're actually able to have differential settlements and movements. So relative movement is allowed. So that's the meaning of these ties. All right? And also the function of this wall is mainly ornamental. It's an architectural intention, but the structure is completely different. So it's not masonry, it's timber. All right? So all the time, bear in mind structure, protections and barriers, insulation and filters, and then architectural expressions and external protections. You will find in all the details, from steel to glass, masonry, concrete, these elements will always be present, whatever you're looking at. What happens when you want to create an opening? When you want to create an opening, this is what happens. You puncture the wall, so you create discontinuity in structural terms and in terms of waterproofing. So what you need to do is simply to restore that continuity. And the structural one is restored through the use of lintels. In this case, there is a steel lintel here, and there is a plate there, and the seal. And waterproofing is restored, placing a couple of flashing elements above. You see the lintel here, and one below. So in this case, you make sure that you have broken a system, structurally and in terms of waterproof protection. Now you restore the original situation. So again, every time you want to create an opening in the wall, you need to make sure that this is working again as it used to do before. Capping on the top, a little bit less interesting, but again, what we want to do, there is a point in which we can actually assess the cavity of the brick veneer here. What we do, we just place a capping, we bring water towards the interior sides and we collect it here. What's interesting to note in this detail is that this is not a timber structure, so this type of brick veneer section works well also if you have steel profiles. So you see that these are steel profiles, but it's actually the same size, the same type of detail, exactly the same. Now, I will encourage you to go and look at this ICA and ZA, which is, I don't remember, I have to read it. I forgot already. That one is the Insulation Council of Australia and New Zealand, where you can find images like these and several others. Not very, I know they're not very interesting, so there is only one image, but you are invited to look at all of the others by yourself. And you see here some details in axonometric views which are more understandable on how to place. You see the stud walls, and then the insulation, the reflective foil, the protection, and then the external layer. So there are several images in axonometric views and perspective view that will probably help you to understand in 3 dimensions how the element works. They also provide thermal and acoustic data. So they tell you exactly how a specific section performs. If you want to look at the U value belongs to the element, so to the material. If you want to look at the R value, which is the one that we see here, the R value, and we see here the total R value, relates to the final section. So when we take this cross-section here and we get the total R value, we cannot reapply the same one to another cross-section. All right? So even if there is the same material and type of things, but no, that depends also on the thickness and disposition of layers. So how the way they are sorted. So the R value you get here can be applied only to this specific section, only with those specific thicknesses and depth of the elements. All right? Generally, the bigger the better. All right? So you understand numerically, quantitatively, how the wall performs thermally. So how it's able to conduct heat. Quickly, concrete blockworks. Concrete blockworks are very similar, but just a bit bigger. And what are the main differences? Let's try to see here. When we have a single leaf, like the one on the top left, it's more or less like a normal brick veneer, but we can add reinforcement because we have these hollow profiles. We're able to add reinforcement both in horizontal and vertical directions We can also use it as a brick veneer. So you see here there is a stud, and then this is just an ornamental and protective layer. Cavity walls, so there is a double leaf. We can also fill in the hollows with concrete. We can pour concrete to make it stronger. So these are the type of differences that you won't find in a conventional brick veneer. And the main advantage, as I already said before, is a matter of size. So the construction is faster. In one block you can place, in the same volume, you can more or less place 6 bricks in size. So whenever you place a concrete block, another person has to place 6 bricks in a course. So you can imagine the advantage. Also, the factory production ensures better consistency of finish and dimensions because they're more manageable. So these concrete things are more precise in shape and cut. As you've seen in the previous slide, integration with steel is possible, so you can actually reinforce it. And it's more efficient in terms of thermal and acoustic performance. Now, again, there are different types. There are manuals and catalogs about that. The only thing I want to show you here is the way they are classified. They are classified according to thickness. So when you get 100 mil, generally the label is 10 point something. When you have 120 mil, the label then is 12 point something, all right? So that's the way they are actually classified and labeled. So according to the depth. You see here that there are different types of shapes, so there is a C shape, L shapes, and also special elements you will probably use for lintels and seals. And what about the joints, the mortar joints? Before we saw already that in the previous slide, there was a guy cleaning up and creating an iron finish. We can also have a flash finish, which is very useful when we want to apply a render on the top of it. And you see some details here that there are some reinforcement rods already embedded in the strip footings. And then you place the concrete blocks. You have some L-shaped elements here at the corners. You have some clean-out blocks here to be able to assist the reinforcement rods. Generally, there is a coupling nut, so they are connected together through a nut. You don't need welding. Lintel blocks, they are generally reinforced so that they can carry more load. You see, this is suspended cantilever, and you can pour concrete in it, so this is a lintel block. How to turn corners. You can have some special elements, L-shaped elements, or in some cases you are lucky because the way you have designed it, you have actually the right dimensions just to place the elements as they are, on the right here. In some other cases you need to split the faces on site. And just a couple of important things and then we'll have a break. Articulation joints and control joints. You know that the house is articulated in several volumes and spaces. Especially with concrete form blockworks, we need to make sure that these elements are at the same time connected but separate. We want them to behave separately. Look at this house. This house can actually do this type of movement, and we don't really want the wall to break exactly in this point. So what we'll do, we'll create an articulation joint. The same happens here. We have 3 main volumes, and these are the type of movements which can occur. This is more of a shear movement, and also see here the elevation. Every time you have an opening, you can have differential settlements, especially due to the footings and foundations. So you really want to make sure that all these wall portions are separate. And in that case, you create an articulation joint. Roughly speaking, look at the elevation of your houses. Every time you have a wall which is longer than 6 meters, you have a problem. So in this case, you see 1, 2, 3, 4, 5, and then articulation joint. In this case, you have a window and a door, so you can make sure that the second one can actually be placed here, or maybe in the middle of the window. That's up to you. It's part of the design, but every 6 meters, so let's say 5 to 7 meters, that's what they say here, you really need to make sure that there are these type of articulation joints. And when you have this single leaf masonry construction, you also add reinforcement inside. And in that case, you don't need the control joints. But what are the control joints instead? The control joints are another type of joint that doesn't relate to the movements of the volumes of the house. It relates to mainly to heating. So let's say you leave the wall under the sun, and then this is likely to expand. So a wall which is long 15 meters is likely to expand so much that it cracks somewhere. So we really need to make sure that we separate portions of the wall and that we have these foam joints, you see one here, that are designed in a specific position where you think is appropriate. I don't know exactly if this project was thought and meant to be there, but if you don't place these type of joints, an engineer or a builder will place them for you. And probably what will happen is that they will be placed where it's more comfortable and not where it's better in terms of design. So it's important you try to think about these aspects before designing a wall which is long 1 kilometer, and then you need to make sure that you actually divide it in several parts. This type of problem happened several times in Zaha Hadid's projects. That she's always saying in interviews that she likes concrete, exposite concrete, because you can actually create all the type of monolithic shapes you want. And that is partially true, because when you have a wall like the Maxi Museum in Rome, which is 16 meters high and 25 meters long, then you have a problem. It's not so monolithic, and you can't really build it that way. So you need to separate it in parts and portions. So somehow your idea that concrete or blocks can make very monolithic volumes, huge volumes, is only partially true. So they have to be divided anyway. Again, you'll find in these sources the information about the R value, so how it performs thermally. And just a couple of examples to show that concrete block works are not so bad. I mean, concrete work blocks have been used by very important architects such as Frank Lloyd Wright. And I went to visit this house in LA, the Ennis House, one of the most famous ones. It was 2006, unfortunately just after an earthquake. So you probably see that the other side was much worse. But you probably see here that the house was almost there to collapse, and there was a construction site, workers there going to renovate it, so they let me in, and I could visit the house. What happens is that Wright decided to use a specific square-shaped concrete block with this type of pattern that he replicated throughout the house, in interiors and also externally. So you see that all the house is completely proportioned on these the dimensions of this block. There is no exception. It has been used consistently. So from that, he actually created all the different proportions of the house. And somehow now they were trying to reconstruct the same concrete blockwork from scratch. And make sure they can create a very similar one to replace the one which were damaged. But these are the new ones which were outside the house. Hermann Herzberger is another Dutch architect who used concrete blockworks a lot. He's not very famous for having done that. It's mainly famous for a book he wrote, which is called Lessons for Students in Architecture, because he was specialized in schools, school design, but not because of school themselves. He was specialized in schools because he was very interested in the idea of dividing public and private spaces. So how these two things interact. You have a public space, a semi-public space, a private space, and you see here this is there is an atrium of a school here, and somehow this interior looks like an exterior. So the idea that there are filters, several filters before going to the most intimate space. Try to understand what happens in all these spaces in the middle. He used concrete blockworks a lot in his architectures to do that. Stephen Hall, just adding these slides to show you how all the elements are always there. So you see the seal, the lintels. If you look at this one, you see it's not a very tectonic detail. So how can we ensure that this brick doesn't fall down? We do that because there is reinforcement inside. But it's not a very tectonic detail. So what happens is that you don't care at all if there are windows or other openings. You just draw the courses normally, and then you place reinforcement and concrete inside so that you make sure it actually stands like a lintel. Look at this interesting seal. This is Ringwood, local architect, very famous local architect, Harry Sedler from Sydney. The interesting part here is that concrete blockworks can also be used to look like masonry, to look like natural stones. So they can actually look like that. I'm not sure if you take a closer picture what happens, but at this distance they can actually be confused for natural stones. Just let me show you these 2 minutes and then we'll have a break, right? Autoclave aerated concrete. There is also a trademark, Aircrete. So what happens here is that it's like a concrete blockwork, but it's lightweight. So the manufacturing process is a bit different. So what you'll do, you have a cement bath, you add aluminium, this reacts, it generates air, and then dries, and you cut it to size using wire. So in this case, you see that you have this section here full of air, so that it's lightweight. And the details are always the same. So you will find reinforcements, single leaves, you see the cutouts with the coupling nuts to connect the vertical reinforcements to the footings. And again, reinforcement embedded in the footings. Structurally speaking, they're not so strong. You won't be able to do a wall out of this without reinforcement. You will always need to place reinforcement rods. Okay, also you see the lintels, how they are reinforced. This is the cross section through the lintel. Just out of curiosity, you can also make floors out of it. They're not very used, but you can have these T-shaped elements and then other blocks that actually generate the floor. And you will see also the R values. You see they're much higher than the previous ones. But let's have a 10-minute break, and I'll meet you back at 20 past 12. Good. Second part of the lecture. We start so that we go home soon. Please, quiet. I'm just going to go through a few pictures of historical examples, and I don't want to substitute myself to any of the historical subjects, but just to make sure that some of the construction principles were touched upon, like, you know, straight away applied to some historical examples, and you see and interpret them from a different point of view straight away, now that you are fresh. So I said before, the most important thing when you talk about masonry is that you think you are creating very static, monolithic, regular objects. As you see from this example, Antoni Gaudí, Spanish Catalan architect, it's actually the opposite, the other way around. Most of the times, masonry has been used to span large spaces, and it has been used to liberate the architect from being constricted by regular geometries. So the overall idea was always to make something ornamental, curved, that could actually span spaces. So these are the two things. In this case, I don't see any specific structural purpose, but it's an ornament. In other cases, it's mainly a structural function to liberate the architects from the regularity. So exactly the opposite of what you would think. And this also, in other ways, it has been used exactly to show what it does in a very tectonic way. This is a very modern building by Andries Petrus Berlage, and the overall idea of this building was that I'm a modern architect. What I'll do, I'll show you the materials for what they are and what they do. So you have very solid walls that are masonry, structural masonry walls, and they sustain a lightweight roof. I need light. I need to let light in. So what I do, I use a steel frame and glass. So everything is done according to very logical, rational tectonic principles. So bricks are used to show that they are a solid wall sustaining a set of arches. Right? More trusses than arches, but just to say, in Amsterdam there was actually a school all dedicated to that, and most of the architects were not really doing acrobatic things, but trying to use masonry really in a very irregular way, try to somehow, you see, to bend it, to make sure that it looks like it falls. Other further details, where you see that it was used in a very sculptural way, especially how to turn the corners and how to create a feeling of verticality rather than horizontality, which is what you get by means of, the courses. Here is exactly the opposite. Vertical lines rather than horizontal lines. Don't you find it interesting that you're achieving exactly the opposite result of what you would generally do? Frank Lloyd Wright was definitely affected by horizontality, so it really was looking for horizontal planes that extend in space, and the type of brick he's using is curiously the Roman one, so very slender, narrow, and even from the back, you see this is not a very common, not a very iconic image, but if you go even closer and take a picture, what's written in the books of history is true. So you see that the pear paints were actually painted of the same color of the bricks, so that you have the feeling of a continuous line of this horizontality. Again, it's a very small, architectural choice, but somehow it makes a difference. And when you look at the image, you see these very horizontal lines everywhere, this redundancy. Again, the arch, it was really affected by the Roman, the architecture done by the Romans, and again he's using arches, one upon the other, just to create an opening. So that would be the most rational way to create an opening without needing lintels. And another very modern architecture, just to make sure that all these architects are modern, of the modernist period, and they're not using steel and glass. What they're using is masonry, so the most ancient material, used in a very modern way. Even this symbol, this icon of the modern factory, of the modern industrial production, is mainly done in steel and glass in terms of opening, but the structure, the structural part, the core, is done out of masonry. The same happens for Mies van der Rohe, probably in an earlier stage of his career. So we probably see that the windows compared to the openings of a traditional house are already wider. So he really wants to say, I want more light coming in, but still you see the structure is made out of masonry also in this case. And Alvar Aalto. Alvar Aalto, Nordic architect. Again, it's very common to say, especially, I've lived in Denmark for 2 years, and mostly the students coming from overseas, they generally go there and say, Nordic countries is, for me, is timber, the idea of timber sustainability. That is not true. In Nordic countries, everything is done in masonry, because that was the material. heavy local material, not timber. In that type of environment, timber will last 5 years. So they don't use timber. They use timber for furniture, they know how to work with timber, they use it for interiors. They don't do houses out of timber, they do houses out of concrete and masonry. I can tell you that. And Alvar Aalto, who is a very modern but at the same time regional architect, shows that. And this is one example, and this is another example, the town hall. And you remember the capping we were talking about before. You say this is a nice way to solve all these details, the lintel and other things with masonry, done by an important architect. You see these details actually is detaching that capping from the wall to create an opening. So every time you have a junction, you have a joint, you try to solve it in another way. So that's what great architects do. Le Corbusier, why am I showing you this? For two reasons. The first is the color of the mortar. So you see that there is a concrete frame, so you see all the floors, they're visible in the facade. Then there is a frame of colors behind, probably one column running here. And what happens is that the mortar is done probably with the same sand, so that the color is very similar to the one of the concrete. And the masonry wall doesn't look so dark. So they actually look very homogeneous. So the final result is very homogeneous. Okay, so this is one thing. The second thing is a little bit more technical. Nowadays, you won't do this probably, because you would get several thermal bridges. So to bring the structure on the facade, as you see in this image on the right, means that you have a direct connection between exterior and interior without insulation. There is no possibility to place insulation unless you literally make a coat, like you place it on the outer side. But if you do that, you won't see the masonry, the concrete anymore. So you need to find another protection. But so if you want to place insulation on the interior side, you will have a thermal bridge here, so which means a loss of heat directly through the structure without possibility of insulating that. All right? So these are all thermal bridges that were probably fine 100 years ago, 60 years ago, 50, not now. Louis Kahn, another guy who actually worked a lot with masonry. You see here the Richards Medical Laboratories in Philadelphia, highly criticized project by the occupants. And again, what's interesting about Louis Kahn is that he's doing very regular, huge monolithic volumes, and what it does to show that they are not so big and heavy is actually removing the corners. By removing the corners, I see that that's a very slender, thin layer, protective layer. So there is not so thick. It's not like 757 Swanston Street, a big monolithic element, our previous faculty. It's a very light one. So he's saying, look, this is the wall, how it's done inside, a very tectonic choice. He's also, always taking, learning from the past, how we would say here. So he's taking different stylistic elements from the past and putting them into modern architecture. He was also a modern architect. Look at this one. This was, for instance, an explicit game of an arch together with a lintel. So anytime you place a lintel like that, you won't need an arch. And when you make an arch, this is already self-sustaining and distributing the forces on the two sides, and you won't need a lintel because you don't need to tie the two parts together. So he's explicitly using the two elements together to make a kind of ornament. It's an architectural decision that doesn't make any structural sense. But again, it's explicit. The idea that you can do these things in two ways. This example, and now I'm showing you a few examples you probably won't know. This is an example from Turin, Italy, the 60s. Iaretti Luzzi were two modern architects. One of that was also my teacher. And they were already in a period which was called brutalism. So the idea that you show the materials for what they are. So you don't care to make them nice and fancy. You just show the brutal part of that. So in order to save money, they weren't really rich, but they really wanted to make nice architecture. What they did is that they rotate the brick vertically so that you see this indentation on the facade. You see the frogs, but you save a lot of material because you put them vertically. So this is one thing. You also see that all the concrete frame is visible in the facade, so you've got a few thermal bridges. And in order to save material, what they also did, they only bought one single formwork to make the columns, because it was very difficult in that period to find circular formworks. So they bought one, it was very expensive, and when they needed more structural capabilities, like in this case, they just double up the column. So they put two columns beside, but just one single formwork. And again, in order to construct, to build one more story, they knew that if you have like incremental cantilevers, you were allowed to build more volume. Don't let me explain the regulations now, but if you do this type of cantilevers, you are allowed to build more volume. So they did that in order to be able to build one further story at the end of the house. And again, Turin, this is Carlo Mollino, a fairly recognized architect for the Royal Theatre, which was destroyed by the war, and he reconstructed it less than 100 years ago. He's using a very ornamental bone for this facade, which is also curved. You won't notice that, but it's a curved facade. And especially the north of Italy, again, is another part in which masonry is used a lot, everywhere. And you see that the heritage that Mollino was looking at was this Palazzo Carignano, the parliament, the old parliament of Italy, in which Guarino Guarini used several types of ornaments. So that was the reference that he was looking at. Aldo Rossi, again in Italy, again in Turin. We are in the postmodern period, but what happens here is that, again, masonry is used to make the big volumes, and then steel renders are used to do the other thing. So steel is always used to make lintels, you see here, but masonry is also used to trace these horizontal lines here, and also up there. But somehow this house incorporates all the elements, traditional elements of Turin, which are like the heavy blocks, the importance of the corner, the portiques, arcades, the seriality in windows, the verticality of the elements. All these are embedded in this architecture. So that's what Aldo Rossi did. If you look at this, at the first sight, it looks like Aldo Rossi is doing the same thing everywhere in the world, but actually he's not. So just make sure that you always analyze carefully what he does, because he's a very local architect. From this point of view, he's really able to apply principles locally. Other details of the same building and combination of materials. The same thing does Adolfo Natalini in Italy. He used to do that. I'm showing you this example because it's interesting to see how control joints and articulation joints are used architecturally. So somehow these type of things can become part of the rhythm of the facade. And Mario Botta looks like Italian, but he's not. He's a Swiss guy. He works together with Galfetti, Snozzi, and Bacchini, the Swiss school. So you see that it can also be used in a very sculptural way to like turn corners. This is called, this is literally an intersection of two circles. It's a religious symbol, which is called literally the almond. So it's a symbol of life. So it's a geometric symbol of intersection of like real and non-real words. So in Italian it's called la mandorla, the almond. Also, you see in the same church how masonry is applied in a very sculptural way. And then we go here. We are in Berlin. You see another control joint here. You see another one here on the left. And then very, very interesting example is that Giorgio Grassi, but also recently Peter Zumthor in Cologne, they've used masonry to renovate buildings, to renovate historical sites. So in this case, we are talking about a Roman theater. Most of the times, what you would do in this type of archaeological sites, you wouldn't touch them at all. You would probably just leave them as they are, as ruins. In this case, it was a very controversial case, but I think it's a masterpiece of architecture, where he actually reconstructed the theater using also some of the ruins. He reconstructed the amphitheater using masonry. Why that? Because masonry, it's a kind of timeless material. So it gives these feelings that it has always been there. Whereas if you use glass and steel, at the first sight you would say it's light, but then it's not. It's a very heavy material. And it really gives the difference between what is old and what is new. Whereas masonry, it really merges in that environment. And I think it's a masterpiece of architecture. Rafael Moneo in Spain, he did a museum related to Roman art, and it's all done in masonry. And what he did, again, it was to take advantage of the traditional principles of the arch, of the Roman bricks, which are very slender and narrow, to create a set of arches and spaces. John Wardle in Australia, he also did a very interesting project early on. What he did was, you see this element here. I think the idea is that you have a straight wall, and as we saw before, there is one thing you cannot do, which is bend the wall or fold the wall. And what John Wardle wants to do with this pattern is to actually give the impression that you are folding the wall. So it's rather interesting to force the limits of masonry in this way. Here you see a detail of what happens. You see there is the need of a special piece to reach this result. Another example here coming from Amsterdam again. What's interesting here is when you look from the bottom and you take this picture here on the right, that you really want to show the chords part of the bricks, so you expose it. So instead of using that for a structural or technical purpose, you use it architecturally. And the same happens in this case. This is a friend of mine, a fairly recognized architect now working in Toronto, Stefano Pugliatti, and the office is called Elastico. What they're doing, they are always based on the principles of Carlo Scarpa, so they really want to show the real nature of materials. And what he wants to show most of the times is the bad, the ugly part of materials. So in this case, he's taking these bricks, and he didn't make a drawing for that. It was just there with the builder, and they were playing with the bricks and tried to put them a little bit randomly to show the roughness, the rough part of this wall. Another interesting case, what he did, look at this hollow brick. He cut them in half, and then he placed them in the facade. So that was the final layer. So he decided that that's what he wanted to show. That's his architectural intention, just to show the ugly part of materials. And also, every time you cut the piece, it will be different. So you see that there is a kind of variety in the facade. You also see a lintel here. But the interesting part of that is that I can also tell you that he used to live very close to a manufacturer, so he was actually kind of inspired by that to try different types of masonry, bricks and things. But you can really do whatever you want. You see a hollow profile, you want to cut it in half and use it in the facade as the final expression of your architectures, yeah, you can do that. And this is one example. All right? This is a closer detail. This project is called Atelier Fleuriste. It's a house for a guy selling flowers. And I'll meet you next week and we'll talk about concrete, Friday at 11. And we'll meet you also on Wednesday for the tutorial. Right? If you have any questions about the lecture today? No? All right, then have a nice weekend.